Hello, everybody. My name is Alexis Ambrise, and my presentation is called Revolutionizing Wireless Communication Machine Learning Meets Signal Processing. This is original research by Jie Yang, Jinghe Du, and Yi Jiang. I really wanted to talk about this topic because as I am learning machine learning and software engineering, um, this is something that's very related to what I wish to do in the future. Um, some background information if you are not from the world of machine learning. Machine learning is the use of algorithms and statistical models to perform tasks such as pattern analysis and prediction without being explicitly reprogrammed. In this article, machine learning refers specifically to the use of artificial neural networks to interpret wireless signals. Signal processing is the analysis and manipulation of signals, which in this context refers to digital signals transmitted through wireless communication channels. Traditional methods of signal processing rely on precise models of the communication environment. A trellis diagram is that model. It is a blueprint of possibilities for how a signal can traverse the airwaves from sender to receiver. It is a representation of the possible paths that a signal's code can take through time as it travels from sender to receiver in wireless communication. It is often used to decode the signals and able to resolve the errors that result from this loss of signal in real time. Finally, the new proposed method of resolving these signals and any errors that may occur with them is the online learning of trellis diagram method, a dynamic intelligence system that uses artificial neural networks to interpret signals. It is an approach to wireless communication that uses machine learning rather than requiring an exact model, such as the trellis diagram, of the communication environment. The system can learn and adapt directly from the signals in real time. So you can think about it as an evolution of the trellis diagram. It is online learning of the trellis diagram. Next up, I'll be talking about the summary of the research abstract. In it, they mention that traditional methods such as using the trellis diagram with ML maximum likelihood and map maximum a posteriori receivers on a trellis for understanding the likelihood. It is based on several state transitions. Both of these receivers utilize the CSI information, which is the channel state information, not CSI like you're a spy, but like CSI is channel state information, and the distribution of the channel noise to do this job of calculating the likelihood of each state transition on the trellis diagram. The authors of this research proposed this new method utilizing ANNs because they thought that needing this channel state information or the distribution of the channel noise at the same time as sending all of this information, it it causes a lot of errors or it could be wasting in time. So sufficient training of an ANN can be used on a pilot sequence to replace this information. So this is an example of the trellis diagram. On the bottom, we have the error resolving um, the error resolving chart where, for example, if there's a bit 00 that goes from this state to this state, it has two paths where it can go in 201 or 11, or it can go the other way into itself and stay at 00, or it can go to 11. And 11 can go to 01, or it can go to 00, 10. So you can see there's many paths that it can take. And the trellis diagram records all these paths as it travels down from the beginning in the sender to the receiver. So signals are this means to send a message, and they must be decoded using some kind of algorithm to encrypt the message, and then that encryption is converted into bits like zeros and ones. And during this transmission of the zeros and ones, errors can result, and there are ways to refer back to the source using a trellis to use the time and the dots. as I mentioned, are the different states. And I picked this image because I think it represents what a trellis is. It is something that supports the transmission of messages. As you can see, this lady sitting below the trellis of vines is using their electronic device to send information, receiving information, sending information, and this proposed method will probably be implemented sometime in the near future. So how is machine learning revolutionizing signal processing, as I mentioned before? So I think that machine learning is revolutionizing signal processing because this novel method is significantly outperform models-based methods that use non-Gaussian distributed channels. They claim it requires less training overhead than the state-of-the-art methods, is quicker, and it actually accommodates turbo equalization, which is something that I don't know what it is, but it's something that exists in signal processing, and it can be applied to a Bluetooth low energy receiver. So the example mentioned in this paper mentions that it only requires a 256 sample pilot sequence. They proposed that this is an enhancement that they added as a byproduct. So it wasn't even a primary goal of theirs, but they ended up doing it anyway. And it even improved the receiver sensitivity farther than they imagined. So this has potential, I think, in revolutionizing IoT communication. Now I'm going to go through the different methods that they talked about in the article. I included some of the charts that they created because I think it illustrates it more than what I can say. So this is the ANN, the neural network. It has two inputs, the imaginary yi, which is one of the bits in the pilot sequence, and then the real yi. So you can think about it, the real is the actual message being sent. The imaginary is a predicted simulation of what that is. Then it uses both and then creates potential transition states that could have resulted in the change from the real to the imaginary. And then over here we have the trellis diagram, which actually models the different transition states and the different states. So this is making predictions of the states. This is holding the states and the transitions, and they work together in real time to capture errors and hopefully not make that many. So as you can see, there are four states, and as there are four states in every transition from one state to another, there's 8 state transitions, since one state can only have two uh, different paths, at least in this diagram, between each point in time. Stage 2 is where they feed the payload into the ANN. Payload, you can think about it as a set of data that is being streamed and then encrypted, decoded, and looks the same as the pilot sequence. Pilot sequence is, you can think about it as the training data. The payload, you can think about it testing, validation, the remaining part of the data that was left out. So part one involved training. The second one involves feeding the payload and then making predictions. The pilot sequence has 8 possible state transition likelihoods for each bit being sent, each yi. And then when feeding the payload, we can assume that it's similar in nature and distribution, or is a larger set of related data. And we can see here, the authors mentioned that there are simulated calculations using their simulated noise function and their model compared to the traditional method. It is actually more efficient, performed better. It only required 1 to 200 training length bits, and it was able to capture all the errors quickly. So the red line, that's the OLTD based model. The blue line, that's the traditional method based model. And this function at the top right, that is the noise function. So you can test that out if you want. Stage 3 is feeding the likelihood into the Viterbi or the BCJR algorithm. These algorithms are using the ANN generated likelihoods for each branch and state transition path of the trellis diagram. Specifically, for BCJR, it performs forward and backward recursion, then outputs LLR. LLR is the log likelihood ratio, and if it's positive, it means that the bit is a 1 when it's decoded, and if it's negative, that means it's a 0. So that's the prediction. A BLE, or Bluetooth Low Energy Receiver, is what is using this information to decode the signal, and it uses the log likelihood ratio to convert the predictions into actual signal. Finally, after decoding, the BER is the bit error rate, which is calculated as a metric to measure if the BLE is doing its job. If it is low, it means that the decoding was successful. If it is high, it means a lot of errors are happening, and the goal is to make it low. And on the left, we can see the author's proposed model, where I'm not a signal processing major, but I think the bit interleavers, what they mentioned having included, created themselves. That gets sent to the modulator. And the beginning, that we have the encoder, which is what's converting the signal into bits, sending it through the trellis diagram. Finally, get to our conclusion. Thank you for watching. Um, before I go, I'm just going to talk about practical applications to using OLTD in a Bluetooth low energy use case, for example, in IoT for Internet of Things on devices using Bluetooth. You can imagine farming in rural areas would benefit with improved IoT for detecting crop growth. In rural areas, there's very little signal, so considering Bluetooth Low Energy devices are technology that don't require to be connected to the internet and is something that's at the heart of many devices we use. From fitness trackers, wireless earbuds, BLE is the thread that ties our gadgets together. The OLTD method is strong, as mentioned in this thread, but also it is very useful because we live in a world that is very interconnected and there's a lot of noise that could result in a lot of loss in signal. So yeah, hopefully this is something that gets implemented. Thank you for watching.